Here we're going to take a look and see how we can solve different types of collisions. We're going to look at elastic and inelastic collisions and see how we use conservation of momentum and conservation of energy to solve given some initial conditions. So in any of these problems, we're typically given the initial conditions and then asked to find out what the final conditions are. Essentially, we can say that the momentum before an interaction takes place is going to be equal to the momentum after it if the system is isolated, if there are no other external forces that are acting on the particles. This is easy because if we look at the internal forces here, the force that one object places on the second object are going to be equal and opposite. Given that they both put an equal and opposite force, the impulse is equal and opposite as we saw before, and therefore we know the momentum before is equal to the momentum after. Doesn't matter how these particles interact, okay? We will always have the same momentum before and after because as they collide with one another, they are going to experience a very, very large force compared to all other forces, and we can ignore any effects such as friction at the moment that the collision takes place. Okay, so again, remember, conservation of momentum applies to the system. Essentially, the system must be isolated. And again, it must be in an inertial frame of reference, meaning that the frame of reference is an accelerator. We can define types of collisions based on whether or not they conserve mechanical energy. Only perfectly elastic collisions will conserve all the mechanical energy. Basically, the kinetic energy is going to remain the same before and after the collision takes place. But in reality, most collisions are not perfectly elastic. Almost all collisions are not perfectly elastic, unless it's happening on the microscopic scale, where it's hard to dissipate energy in the form of friction. In elastic collisions, some of the mechanical energy is lost. So we only have conservation of momentum to go on when we're calculating this. It means that essentially that mechanical energy that was there before the interaction took place, some of it has been taken up by some non-conservative forces, friction, some of it's been converted into sound, and we can't say the energy before equals the energy after. In the perfectly inelastic collision, however, if they're bound together after the collision's taken place, their final velocities are going to be the same, and therefore, at least we'll only have one unknown to solve for. So again, elastic collisions are classified as conserving mechanical energy. A good example of this is the case of billiards. And with pool, you are losing some of the energy. Some of the energy is lost. You can hear the collisions taking place. You can hear the interaction between the balls. However, it's important to note that most of the time, this energy is fairly small, and we can ignore these losses and treat it like an ideal situation where it is elastic. However, in inelastic collisions, there is quite a considerable amount of kinetic energy that's lost. In the case of a perfectly inelastic collision, you're really losing some of the really maximum amount of kinetic energy for that type of interaction. Tackle in football is a good example of an inelastic collision. Two players come together, one tackles the second, so they're bound together after the collision has taken place, and their final velocity will be determined given what their initial momentum was. So perfectly elastic inelastic collisions, the math becomes slightly simple, okay? Instead of just having the momentum of one plus a momentum of two before the collision equals a momentum of one plus a momentum of two after the collision, we can actually simplify it and say that the final momentum is m1 plus m2 times the final velocity because they both move together. There is no velocity for one and velocity for two. And essentially, that means that you only have one unknown to find if you have the initial conditions. Let's do an inelastic collision. In this case, two cars are colliding here. One is an SUV with 1,800 kilograms of mass, traveling at 15 meters per second, and the other is a 900 kilogram car traveling in the opposite direction with the opposite velocity of negative 15 meters per second. The cars collide head on. And as they do so, after the collision takes place, their bumpers lock up. However, because the SUV had much more momentum, okay, with twice as much momentum, the two cars will lock together and move in the positive X direction after the collision has taken place. Now, right after the collision has taken place, all the momentum before is equal to the momentum after. They will eventually slow down as non-conservative forces like friction bring them to rest. But at the moment of the collision, right when the collision has ended its exchange of momentum, the impulse is zero between the cars. That's when we will have conservation of momentum, and the momentum before equals the momentum after. So again, we take our perfectly inelastic collision equation. We're going to solve for the final velocity. By solving for the final velocity, it's just the sum of the momentum before divided by the total mass. In this case, 1800 times 15 plus 1900 times negative 15, okay, gives me 2.7 times 10 to the 4 minus 1.35 times 10 to the 4. Of course, that's going to be 1.35 times 10 to the 4, since the car had half the momentum of the SUV. We divide this by the total mass, and not surprisingly, after the collision takes place, the two vehicles are traveling 5 meters per second in the positive X direction. Now, if we do a kinetic energy analysis of this, it's not all that hard. Both cars were traveling with the same speed, so the total kinetic energy before the collision would have been 1/2 the total mass, 1800 plus 900, times the velocity squared, because 15 squared is the same as negative 15 squared. We would be able to calculate the total kinetic energy before the collision. After the collision, the mass still remains the same, still 1/2 mv squared, but now the new v is 1/3 the original v. So at 1/3 the original v, we're down to 1/9 the amount of kinetic energy. So we've lost a little bit less than 90% of the total energy in the system during the collision. And where did it go? It went into deforming the two bodies as they collided into one another. Now, again, we have to be very careful here. Momentum is a vector quantity. Direction is very important. Look at how I did these problems right here. I made sure that my car traveling from right to left had a negative velocity and thus a negative momentum. I made sure the SUV traveling from left to right was moving in the positive direction, giving it a positive momentum. And essentially, when I look at the final results here, I know the two vehicles are locked up and traveling in the right direction, traveling from left to right rather than from right to left. Obviously, if the car had more momentum than the SUV, after the collision took place, they'd be both traveling to the left rather than to the right. My final velocity would be negative, but again, it's positive in this case. Now, elastic collisions, we conserve momentum. So here's my momentum equation right here. And we conserve kinetic energy. We would think that it'd be very difficult to combine both equations together and get a meaningful result, because one is the first power velocity, the other one's the second power velocity. However, when we combine the two equations, we actually get a very simple result. And we get the fact that the difference in the initial velocities of the two masses before the collision is equal and opposite to the difference of the final velocities after the collision takes place. Or if you want to write it a different way, the sum of the velocity before and after of the first mass is equal to the sum of the velocity before and after of the second mass. We're going to use this first expression right here in order to conserve energy, conserve kinetic energy, and try to predict how this is going to behave. Okay, so let's do this problem here. We're going to have two masses, One is 8 kilograms. The second one is 5 kilograms. They're both traveling with a speed of 10 meters per second. The first mass is traveling to the right, so positive 10 meters per second. The second mass is traveling to the left. Negative 10 meters per second is our velocity. So we look at the initial conditions before. We want to find the final conditions after the interaction. Okay, so I start with this equation here, and I know my initial conditions. I'm just going to plug in to get a relationship between my two final conditions. So initially, mass 1 is traveling at 10 meters per second. I subtract off the velocity of mass 2. That's a negative, so I'm subtracting by a negative number. So I'm going to get a positive 20 on this side. And then on this side, I still have negative V1 final minus V2 final. Okay? So that equals 20. I flip the negative sign. So now I get V1 final minus V2 final equals negative 20. And I want to put one in terms of the other. I want to put one of the velocities in terms of the other because I'm going to plug that into my conservation of momentum equation. So now let's go ahead and do that. I put my V2 on the right-hand side. I have negative 20 also on the right-hand side. Okay, just adding V2F to both sides. And here's my first expression right here. I have two unknowns. I can't solve for that. I need a second equation, and I'm going to use conservation of momentum. Here's my second equation right here. And that equation right here simply gets plugged in where you see V1F right there, right? What that does is it takes V1F, one of my unknowns, out of the equation, leaving me with only V2F, and I know I can solve for that. So once again, my left-hand side of the equation doesn't change. Here I've made my substitution, okay? Now I plug in the numbers. M1 times V1I is 8 times 10. M2 times V2I is negative 5 times 10. And then we have 8 times negative 20 is negative 160. And M2 is going to be 5 times V2F, but I have also 8 times V2F, and that gives me 13 kilograms V2F. All right, all I have to do now is put my V2F term on one side, put all the other terms on the other side. I get that 13 kilograms times V2F equals 190 kilogram meters per second. Divide both sides by 13, I get V2F equals 14.6 meters per second. So I know the final velocity of this. Once I have that, I simply go back to this expression right here. I have V2F, so I can plug that, that 14.6 for my final, add that to 20, and I get negative 5.4 meters per second. So you can see here, the two come in with the same speed, they bounce off one another, okay? The second one ends up with much more velocity than the first one, actually speed, if we're talking about absolute velocity, okay? But we still are able to conserve kinetic energy, right? We still conserve momentum in this case. Okay, so in summary, elastic collisions, both momentum and kinetic energy are conserved, but perfectly elastic collisions are ideal, an idealized system. In inelastic collisions, we can only use conservation of momentum, but if it's perfectly inelastic, the two final velocities will be the same, as we saw with that collision of the SUV and the car. Okay, let's jump to another problem. Again, here's our elastic problem where they bounce off one another. We're going to look at a system where we have a perfectly inelastic collision. They're going to stick together, and then we're going to combine conservation of momentum with conservation of energy. It seems strange that I would do that after telling you energy is not conserved in a perfectly inelastic collision. What I'm going to do is I'm going to collide two things inelastically, and then I'm going to use their momentum to convert kinetic energy into potential energy. So yes, the inelastic collision, you do not conserve energy. But after the collision has taken place, these two objects which have stuck together do have some energy, and that energy is going to be conserved and converted from kinetic energy to potential energy. This is what we call the ballistic pendulum. And this dates back to an era when they were trying to characterize the velocity of bullets, the velocity of cannonballs, the velocity of any projectile fired from a gun, but they didn't have high-speed photography in order to, measure the exact velocities. They were just moving too quickly to time them properly. So they figured out a way to create an inelastic collision where the bullet or cannonball would be captured by some device. For the bullet, could just be a wooden block. If it were something like a cannonball, they'd probably use something a little more substantial than a wooden block. It'd blow the wooden block apart. This was usually something that almost looked like a vase. It would capture the cannonball would rattle around inside of it, but it would still move up after being hit. But in any case, what they would do is they'd fire the bullet into the colliding material. The initial block was much more massive than the bullet. After the collision, the momentum from the bullet is now transferred to the block bullet system. And with the same momentum, but at a much lower velocity, we would convert the kinetic energy into potential energy. So here's how it would work. Bullet hits the block containing bullet swings upward. It's a pendulum. And the height at which the block would swing to would give you an idea of how much kinetic energy that the system had after the collision took place. So we could use the height to determine the kinetic energy after the collision, not the kinetic energy before, but the kinetic energy after the collision. And then from that kinetic energy, we could see how fast the block bullet system was moving, and then get the initial momentum from that and the initial velocity. So first of all, phase one, we start out with an inelastic collision. The bullet is traveling with a mass small m, velocity v1, hits the block. Energy is not conserved here, okay? A lot of the energy, the mechanical energy, is lost as the bullet slows down into the block. The block itself starts with no velocity, so its velocity is 0, its mass is big M. So we say mv1 plus mv1, okay? This mv1 is 0 anyway, it's not moving. The momentum before the collision is going to be equal to the inelastic collision momentum after the interaction has taken place. So bullet plus block afterward is going to be my final momentum. Momentum is conserved. So we can calculate how fast the block is going to be moving after this interaction has taken place. It's important to note here that big M has to be substantially larger than small m. Otherwise, the block will be given so much velocity that it will essentially swing beyond mechanically what makes sense to it. So again, whatever we're firing the projectile into is going to be significantly more massive, but not so massive that the height that it swings up won't be measurable. So again, block and bullet now are moving with a velocity of mv1 over m, small m plus big M. Now, here's where energy is conserved. The collision did not conserve the energy, but this is essentially a pendulum system where we know the kinetic energy is greatest at the bottom of the swing. It's 0 when it reaches its highest height. So all the kinetic energy initially is going to be converted into potential energy finally. So we can write this as 1/2 small m plus big M times v2 squared, okay? That's kinetic energy that it had at the beginning. It is going to be equal to small m plus big M, g times h, which is the height at which the pendulum swings up. Okay? Simplifying this further by dividing mass on both sides, we get 1/2 v2 squared is equal to gh, and h equals v2 squared over 2g. So how do I get from this height my v1 again? Well, I simply work backwards. if this is my height, given a velocity of bullet and block at the bottom of the swing, the velocity of the bullet and block at the bottom of the swing was square root 2 hg. And I know that V2 was also equal to m V1 small m plus big M, okay, divided by small m plus big M. So I'm going to plug or set these two equations equal to one another, solve for V1, and I get that the speed of the bullet will be equal to the ratio of the mass of the block and bullet compared to the mass of the bullet. Again, you want this to be large compared to this, times the square root of 2 hg, and that'll tell me how fast that bullet was traveling. Very ingenious method to actually measure the velocity of something that you can't see because it's traveling too fast. And again, inelastic collision where energy momentum is conserved, energy is not, and then a swing of the pendulum where mechanical energy is converted from kinetic to potential energy.